two dangerous snakes into the nursery. They coiled around the crib, clicking their tongues. Iphicles woke up and screamed. Hercules woke up, sat up, and grasped the two deadly serpents by the throats. The creatures struggled, wrapped around Hercules' body, but he held them tightly. Alcmene heard Iphicles' screams, and she rushed into the nursery. To her surprise, she found Hercules sitting up in the crib, laughing loudly and holding a long, limp body in his hand. Their father entered the room and inspected the snakes. They were dead. Both his parents knew then that Hercules was destined for greatness. Hercules received a good education, but he had a few accidents along the way. He accidentally killed his music teacher by lightly tapping him on the head with a wrench. Hercules was very, very sorry, but that didn't stop him from doing the same thing again and again, because he just didn't realize his deadly and powerful strength. Hercules grew up, and he surpassed all other men in strength and skills with weapons, but he was constantly hounded by the jealousy of Hera. She couldn't kill him. Since he was Zeus's son, he was immortal, so she vowed to make his life as miserable as possible. Hercules married the princess Megara. You know how difficult it is to find any picture of these people where they're wearing clothes? Hercules was devoted to Megara and their 3 sons, but this marriage brought him the greatest sorrow of his life. Vindictive Hera hated that Hercules lived in joy with his family, and she sent an insanity upon him. Struck by the madness, he killed his sons and his wife as she was trying to protect the children. When his sanity returned, he found himself standing beside the dead bodies of his family. He had no idea what had happened, and he demanded to know how they had been killed. One of the witnesses told him everything. Hercules was so devastated that he wanted to kill himself, but his friend Theseus managed to talk him out of it, although it took a long time to do. Hercules then went to see the oracle of Apollo. She told him that he needed to be purified, and only a dreadful penance could accomplish that. She commanded him to go and see King Eurystheus, and to do whatever the king demanded. Hercules was ready to do anything. King Eurystheus devised a series of penances that are known as the 12 labors of Hercules. Eurystheus had help in dreaming up penances. Hera helped him. She had never forgiven Hercules for being Zeus's son. The first labor involved killing a monstrous man-eating lion that was terrorizing the countryside. Hercules tried to kill it with his arrows and his club, but the lion's hide was so tough that the weapons all broke to pieces. Hercules managed to strangle the lion with his bare hands, succeeding in his first task. He used the lion's own claws to cut off its skin, and for the rest of his life, he wore it as a cloak, and he wore the helmet, the head as a helmet, which made him look even more scary than he really was. And now we know this lion as the constellation Leo the Lion. When he returned to Eurystheus, the king ran away in terror at the sight of the monster. He ordered Hercules to go away and come back only when he was told to do so. Eurystheus was a cautious man. Actually, he was a coward. He had a specially fortified room that he could run to when Hercules looked too frightening. The second labor was to kill a hideous monster called the Hydra. This creature had 9 heads, and it lived in a swamp. It made its meals out of careless people that wandered too close. Hercules shot a fire arrow into the Hydra's den to lure the monster out. Killing the Hydra was going to be easier said than done, since one of the heads was immortal, and the others were almost as bad. As soon as Hercules chopped off one head, 2 more grew to replace it. To make matters worse, Hera set a large crab scuttling out of the swamp to attack Hercules' feet as he fought the Hydra. Angrily, he stomped on the crab and killed it. Hera rewarded the brave little crab by putting it in the sky as the constellation Cancer the Crab. Then Hercules got the idea to burn the stumps as each of the Hydra's heads was chopped off before another one had time to grow. This was quite a second labor. Before he left, he dipped his arrows into the hydra's poisonous blood. Eurystheus then sent Hercules to capture a stag that was sacred to Artemis, the goddess of the hunt. This was less a test of strength, nor a test of endurance. The stag led him on a year-long chase before it was too tired to run anymore. Hercules tied the stag's legs, hoisted it around his neck, turned around, and walked back into Artemis. Hercules kept his cool, he did a little bargaining, and he was allowed to carry the stag back to Eurystheus, provided it was returned to the forest. Thus ended the third labor. Then the king sent Hercules to Erymanthus to kill a wild boar that was terrorizing the area. Every day the boar would come crashing down from his lair on the mountain, attacking men and animals all over the countryside, gouging them with his tusks and destroying everything in his path. On his way, he passed through the region of the centaurs. When one centaur offered our hero some wine, the other centaurs got jealous. Now, a few centaurs are refined and well-educated. These ones were not. The great brawl erupted, and Hercules defended himself with his club and his poisoned arrows. Then he continued on his way. It was winter when Hercules found the boar. It wasn't too hard for him to find it. He could hear the beast snorting and stomping as it rooted around looking for something to eat. Hercules chased the boar around and around the mountain, shouting as loud as he could. The boar, frightened and out of breath, hid in a thicket. Hercules poked his spear into the thicket and drove the exhausted animal out into a deep patch of snow. He caught it, tied it up, and took it back to Eurystheus. The king's reaction was to hide for a week in his fortified room. The fifth labor was clearly impossible. Augeas, the king of Elis, had many horses, cattle, goats, all kinds of livestock. The manure had gathered for 10 years. The smell was so bad that nobody wanted to go near it. Hercules was ordered to clean this up. Fighting monsters had never looked so good. Hercules accomplished this task by diverting 2 rivers to run through the stables, cleaning them in less than a day. First, the hero tore a big opening in the wall of the cattle shed where the stables were. Then he made another opening in the wall on the opposite side of the shed. Next, he dug wide trenches to 2 rivers which flowed nearby. He turned the course of the rivers into the yard. The rivers rushed through the stables, flushing them out, and all the mess flowed out of the hole in the wall onto the other side of the yard. Hercules' 6th labor was to destroy a flock of flesh-eating birds. Hercules wasn't afraid of the birds, he just had trouble finding them. Athena helped him by giving him a giant brass rattle. When Hercules shook it, the noise sent the birds into the air by the thousands. Hercules shot arrows at them and killed them all. The 7th task involved capturing a bull on the island of Crete that was destroying the countryside. Hercules wrestled with the bull barehanded and brought the animal back alive to Eurystheus. The spineless king ran away in terror. This bull is now in the sky as the constellation Taurus Low. Next, Hercules traveled to Thrace, which was ruled by King Diomedes. King Diomedes had one kind of icky flaw. He liked to feed his horses human flesh. When Hercules conquered him, he fed the king to his own horses. Then he brought the horses back to Eurystheus. Eurystheus hid and ordered that the horses be taken to Mount Olympus and given to Zeus. Hercules' 9th labor was to capture the belt of Hippolyte. This was no ordinary belt and no ordinary warrior. Hippolyte was the queen of the Amazons, a tribe of women warriors. Queen Hippolyte had a special piece of armor. It was a leather belt that had been given to her by Ares, the god of war, because she was the best warrior of all the Amazons. She wore the belt across her chest and used it to carry her sword and spear. Eurystheus wanted Hippolyte's belt as a present to give to joined with him and set sail in a single ship. After a long journey, they reached the land of the Amazons and put in at the harbor. When Hercules and the Greeks got off the boat, Hippolyte came down to visit them. She asked Hercules why he had come, and when he told her, he promised to give him the belt. But the goddess Hera knew that the arrival of Hercules meant nothing but trouble for the Amazons. Disguised as an Amazon warrior, Hera went up and down the army, saying to each one that the strangers who had arrived were going to carry off the queen. So the Amazons put on their armor. The women warriors charged down on horseback down to the ship. But when Hercules saw that they were wearing their armor and were carrying their weapons, he knew that he was under attack. Thinking fast, he drew his sword and killed Hippolyte. Then he undid her belt and took it away from her. Hercules and the Greeks fought the rest of the Amazons in a great battle. When the enemy had been driven off, Hercules sailed away. After a stopover at the city of Troy, Hercules returned home and he gave the belt to Eurystheus. The 10th labor was to travel west to kill Geryon, a giant with 3 bodies and 3 heads. The giant lived peacefully with a herdsman and his 2-headed dog, tending large herds of cattle. Eurystheus wanted the cattle, but without the giant. The dog and the herdsman were easy to kill, but the giant had to be killed 3 times, of course. Hercules traveled home, driving huge herds ahead of him. While Hercules was sleeping, some of the cattle were stolen by Cacus. Hercules tracked down the cattle to Cacus's cave. Did I mention that he was another giant? One that could breathe fire and had a trophy room full of his victims' heads. Well, one blow of Hercules' club and another monster was dead. When Hera had married Zeus, he gave her a tree that grew golden apples. She was so delighted with it that she placed it in the garden on the slopes of Mount Atlas. She hired the 3 daughters of Atlas to guard the tree, but they were untrustworthy. They kept picking the apples and eating them. So Hera set the dragon Ladon around the tree to stop any further pilfering. Only Atlas was allowed to approach the tree. Hercules' 11th labor was, you guessed it, to steal one of the apples. We've all seen the pictures of Atlas carrying the world on his shoulders. Hercules offered to carry it for him while Atlas stole an apple. Ladon was catnapping when he heard the footsteps of Atlas. He glanced at his master and went back to sleep. Atlas took an apple, and then he realized that he no longer had to carry the world on his shoulders. He told Hercules that he would deliver the apple himself. Hercules said that he didn't mind carrying the globe, but first he'd like to go and get a shoulder pad to lean upon. Atlas took back the world. Hercules quickly grabbed the apple, laughed at Atlas, and ran away out of the garden. Hera was angry because the dragon had failed to protect her apples, and she punished the dragon by placing him up among the chilly circumpolar constellations, never resting, never setting. Poor Draco the dragon. The 12th labor was the most difficult. Hercules was sent to the gates of the underworld to fetch Cerberus, the 3-headed watchdog. Cerberus had the head of a dragon, and his back was covered with snakes. Hercules was protected by the skin of the lion, and he managed to wrestle Cerberus with his bare hands. He had 2 of the throats in his vice-like grip and dragged the dog back to Eurystheus. The startled king had never expected to see Hercules alive again, but with all of his labors completed, the king had no choice but to make Hercules a free man again. The death of Hercules is a piece of true Greek tragedy. After his labors were completed, Hercules married Deianira. While they were traveling together, they came to a river where the centaur Nessus ferried passengers across on his back. Hercules swam across the river, and Nessus carried Deianira. The centaur made a pass at her, and Hercules shot him with one of the arrows that had been dipped in the iron blood. The dying centaur offered Deianira some of his blood, saying that it would act as a love charm. Innocently, she accepted the poisoned blood and kept it safely away until much later when she suspected that Hercules had his eye on another woman. She hoped to rekindle his affection, so she gave him a shirt on which she had smeared also being hunted by Hercules. Hercules' brightest star is called RASC Winnipeg, which is Arabic for the Nealer's Head. This is a red supergiant that varies in magnitude from 3.1 to 3.9. In a telescope, you'll see that it has a fifth magnitude companion. Now, this is just an optical double. The two are not physically related. And the companion is a binary, but the two are too close to be split by our telescopes. What you will see is a beautiful red and green pair. It's an easily split double star. One of the best-known objects in the sky is globular cluster M13, which we call the famous Hercules cluster. This is a faint fuzzy. It's about 2/3 of the way up the western side of the keystone. On a really good night with no light pollution, you might be able to see M13 naked eye. In binoculars, it's a bright round globe, and in a telescope, it's very large. It's 23 arc minutes in diameter, and you can resolve stars completely across the center. The dense broad center is very bright and sparkling, and the outer stars cover a diameter larger than the full moon. M13 was discovered by chance by Edmund Halley in 1714, and it was rediscovered by our friend Charles Messier in 1764, although he couldn't resolve any stars in it, which is a comment on the quality of his telescope. M13 is one of the most prominent and best-known globular clusters, and it's one of the first deep sky objects that most people look at. It is home to hundreds of thousands of stars, and it spans over 150 light years across. While you're in the area, take a look half a degree to the northeast. This little galaxy, and you see 6207. It measures 3 by 1.2 arc minutes, and its magnitude is 11.6 with a bright core. It's kind of small, and it's not really all that interesting, except for being so close to M13. You'll still see a little bit of glow from M13 at the edge of your eyes. It's that close. Another really nice globular cluster is M92. It's almost as bright as M13, but it's only half as big. It's 11.2 arc minutes across. Its magnitude is 6.5, and in a telescope you can resolve stars almost to the center. This is a very pretty object. Charles Messier discovered M92 in 1781, but he couldn't see any stars in this one either. There's another really teeny globular cluster, NGC 6229. It's very faint compared to the other two. It's only 10th magnitude. Hercules has a pair of colliding galaxies called ARP 272, whatever ARP means. This is a pair of interacting galaxies. The two spirals are NGC 6050 on the left and IC 1179 on the right. ARP 272 is about 450 million light years from Earth, and these other ones in the picture are just background galaxies. They're not part of the system. NGC 6210 is a relatively bright planetary nebula. It appears as an out-of-focus blue-green star, and it's sometimes called the Turtle Nebula. It was discovered in 1825 by the German astronomer Friedrich Georg Wilhelm Struve. Its distance is estimated to be about 6,200 light years away, and it's about a half a light year across. It's estimated to be about 2,000 years old, so it's really rather young for a planetary nebula. It contains a wide range of filament structures and jets. Telescopes will show you a blue-green color due to the high surface brightness of the nebula. With at least a 12-inch scope and averted vision, you may see the outer region that covers 20 by 13 arc seconds, and the central star should be visible in an 8-inch scope. Right now, Hercules is still fairly high, so now is a good time to get out there and take a look at it.
from far away, wish I could be with you in person, but it's really nice to be here and to meet all of you virtually. Thank you for the kind introduction. I still feel like a new Canadian, but I'm now in my 6th year in Canada, which is great. And I'm going to speak to you a little bit about the background and my motivation for all of the work that I do. And then, of course, as Judith said, I will highlight the Rubin Observatory, which is sort of been my guide star throughout my career. The first paper I ever wrote as a student was about science with the Rubin Observatory, and we are now tantalizingly close. Rubin will see first lights next year, so it's very, very exciting. But let me not get ahead of myself. I'll start at the beginning. So I am a little bit biased. I'm a child of the Southern Hemisphere from South Africa, and so I always like to open with a picture of the large and small Magellanic clouds that not everybody can see from the north. But you know, we come from a long line of people who have looked up at the sky and wondered how it all fits together and how what the universe is made of and what makes it tick. And I'm really lucky that my job involves putting together the puzzle pieces of the universe. We want to understand the universe from its very beginning and its evolution through time. And we have a limited set of data available to us, and we sort of have to do the backwards propagating and the detective work to try and piece all the pieces together. So I see my job really as building puzzles, where the puzzle is the model of the universe, and we have all these fragmented pieces from observations. If you're ever lucky enough to get a cartoon version of yourself, so this is a really fun video I worked with the TED team to make a sort of cartoon version of the universe, and they also have kindly added me to the video. But what I love about this video is it describes just in a short period of time really the gist of what I study, which is that using equations first derived in completeness by Einstein, we really can take very few fundamental parameters, and if you tell me what the values of those parameters are, I can actually tell you almost everything in the life of the universe on the largest scales. I can't necessarily tell you how a galaxy will form or where in space it will form. But statistically, I can describe pretty deterministically everything that will happen in the universe, which is really a marvel. We have a pretty good picture of when things happen in the universe. And one of the reasons why we can do that is because Einstein's innovation was to realize that the content, the energy content of the universe, the mass, the radiation, the dark energy, which we'll get to, that curves space-time. So if we give up the notion that we have 3 spatial coordinates and 1 time coordinate as being separate, and we instead integrate that into the concept of space-time, then if you tell me what the universe contains, I can tell you how the space-time will shape, the shape will change, and then that space-time curvature tells matter how to move. And so in this picture here, you have a satellite orbiting the Earth. It's not held together by some invisible force. It's actually moving in an orbit that's defined by the curvature of space-time, and that curvature is distorted by the presence of the Earth. And this beautiful synergy is really the driving force behind a lot of our cosmological measurements, and it's this beautiful simplicity that I think is not always present in other branches of astrophysics, because there's this overarching large-scale simplicity and linearity, we'd like to say. But, you know, so I've told you that we have this beautiful theory, I've told you that we can make predictions for the future of the universe, but what is the universe made of? Cosmologists love pie charts about the universe, and one of the pie charts that we like to show is this accounting, this pie chart of the total stuff in the universe. Because we have E equals mc squared, the one equation that everybody knows that relates the mass of something to the energy through c squared, right? And the reason why that equation is so important is it means I can now compare the energy of mass to the energy of radiation and to the energy of everything else. And so when, as a cosmologist, we don't talk about the mass of stuff in the universe, we talk about the energy of stuff in the universe because we're considering everything together. And then I can talk about how much of the total energy in the universe is made up of various components. And if we do that accounting, the first thing we realize is if we add up all the stars that we know, all the neutrinos, all the planets and the moons and all the gas in the universe, we get to roughly 4 or 5% of the total stuff. You may ask how we measure the total, and we basically constrain that through observations, but we have left with this big problem, which is that only 5% of the universe consists of stuff that we understand very well, the stuff that has been well studied for hundreds of years. We have 25% of the remainder, or 25% left of the pie, that's made of dark matter. I'll go into a little bit more detail about what I mean by dark matter. But the shorthand that you can use if you want to have a tagline for dark matter is I like to think of it not as dark matter, but as invisible matter. Matter that's not interacting with light. But in every other way, it behaves like normal matter. It clumps. You could have it, you could imagine having a dark star, but the problem is dark matter is not interacting with light. It's very different from the rest of the pie, which is the remainder of the pie is in fact dark energy. Dark energy, the only thing common between dark energy and dark matter is the word dark. A lot of people get them confused because we stupidly put the word dark in both of their names, but dark energy you can think really of as a sort of anti-gravity force, and I'll go into a little bit more detail about what that means. But both dark matter and dark energy, the dark here refers really to our ignorance. We are looking and thinking critically about what dark matter could be, if it's a particle, and really evaluating our theories as to what dark energy could be, because it's definitely not a particle like we might be able to detect on Earth. So how do we measure dark matter? It's interesting to think about that you can only see me today because the atoms in my skin are reflecting the light in the room. I love this picture. This is just of a mirrored building, and so most of the stuff that we know we call baryons. So you, me, planets, the ground, and the sun. And baryons either make their own light, so they shine like the sun, or they reflect light, like the particles of my skin. And this property of interacting with light, generating your own thermal radiation or reflecting light, is really central to our ability to detect baryons in the universe, because they either shine or they reflect. However, dark matter doesn't do that. And so we can't look for it in the same way. It's not going to be reflecting light or making its own. Nice analogy again from the southern hemisphere is if you look at this giraffe, in this image it is reflecting scattered light, but if you look at it in infrared, of course it is emitting thermally. And so that's the critical difference between that and dark matter. Dark matter, we need to find other ways to look for it. Now some of you may go for a glass of wine after the talk, and if it's a nice moody evening, you will take your wine glass and hold it up in between your eye and the candle flame. Depending on the angle that you tilt the lens, you'll notice that you either have a full circle, sort of like a real circle of light, or you'll have a couple of arcs. Now, one of the great things about optics, optics is just really telling us what happens if I change and distort the path that the light travels on. And if you actually measure these white arcs of light, I can actually tell you, if I make that measurement, I can infer properties of the lens, of the bottom of your wine glass. And that's just a property of optics. We can do the same thing, however, in space, because what we see is that there is a lot of matter in the universe that is distorting the light of galaxies behind it. So this is an image from the JWST, which launched recently. It's a beautiful picture. It takes the Hubble Space Telescope diagram image of the same patch of sky and blows it away. Apologies, I have a curious cat next to me. And what you see here is in the foreground, you see sort of blobby galaxies. In fact, this is a cluster of galaxies, and they are in between us and the distant galaxies in the background. And they are very massive. And then if you look, at the background galaxies, you'll notice that there are these beautiful streaks. And these streaks, in fact, are background galaxies whose light has been distorted in exactly the same way that the lens was distorting the candle flame. And in fact, you can see, in some cases, you can even see copies of galaxies, because you're seeing more than one copy in the same way that in this case, you're seeing more than one copy of the candle flame. So this is incredible. It's one of my favorite concepts in cosmology, that we see this relatively simple picture of optics, and we can reverse engineer the mass of the stuff doing the distortion, doing the lensing, by looking at these images. Now, because I know about how massive things shine, so how stars shine, I can also measure the mass of the stuff in the foreground in this image, so these orange fuzzy blobs, by sort of counting how bright this is and estimating roughly how many stars must this be, and so I can estimate the mass. And the problem is, if I add up the mass that I can see in light in these orange blobby galaxies, and then I measure the mass that must be present because of the distortions in lensing of the background galaxies, the two don't add up at all. You have way, way, way more matter that you need to be there from the lensing signature than you can see with your eye. And so this is one of the big evidences for dark matter, because the stuff doing the lensing is dark in the sense that it's not visible. And so we infer dark matter that way. This is the bullet cluster. It's another example of the same thing. In this case, the lensing signal is not as severe, so you don't see these huge arcs. But you will notice that there's a little bit of distortion in some of the galaxies. And in this case, you see two clusters of galaxies that have actually interacted. And the stars in the two clusters, they sort of pass through each other without really interacting much, which is the same that will happen to us when we eventually collide with Andromeda. No single star will hit another star. The stars are pretty far apart. However, the gaps in the two galaxies will be distorted. And in this case, we have to go to X-ray light to see the gaps. So here, what we've done in this blue sort of false color image, I have estimated where the dark matter must be based on the lensing signature that you see with these galaxies. So again, you just measure the sort of wibbling and stretching, and then you can measure where the dark matter should be, and you get a map like this. But if we want to look at the gas, we need to go to X-rays, and now the picture looks something like this. So this is something like the Chandra X-ray telescope, and you notice this big, it's called a bullet cluster, because it really looks like there's a bullet that is hitting through this gas. And so if we put all of these images together, you can see a much more complicated picture emerging. So the dark matter has really passed, these two clusters of galaxies have passed through each other unscathed, and the gas is what's really interacting. And this gives us more evidence that dark matter doesn't really interact with light, doesn't really interact with baryons, but it is ever present in these huge clusters. And in fact, dark matter is really all around us and is everywhere in the universe. I haven't really told you what it is, and we live in this duality between theory and observation. Often we make observations that suggest that dark matter is present, and then we need to think about what it could be, and some of my work is doing that. And one of the proposed ideas for dark matter is that it is in fact a scalar field. So could it be an ultralight scalar field? Well, we need to first think about what is a scalar field. An analogy that I like to use is if you're all sitting in a room, you are in 3D space, and if I measure the temperature at every point in space in that room, then the temperature is a scalar field. So scalar just means that I only need one number to describe it, the value of the temperature, as opposed to a vector where I would need a magnitude and a direction. But if I record the value of the temperature everywhere in the room, it is a scalar value that is varying in space, and so that's a scalar field. You might be more familiar with the concept of a scalar field from something like the Higgs boson, and in fact in axions, we're considering a scalar field that's moving in the universe. So its dynamics is actually going to change the behavior of the scalar field, and it's going to then change the energy density that we see. And so the way that the field behaves and evolves with time is we talk about it being set by a potential. In this case, the potential has a very specific shape. And the axion field, axion particle, axion field is very ultralight field, is going to change the way the universe behaves with time. When I say ultralight, what do I mean? Well, we don't like to have pesky, complicated units with lots of zeros, and so when you're moving to the very light or the very small, you often can convert kilograms or grams into easier units. So in this case, we talk about electron volts or EV. And EV, if you convert it into kilograms, is basically 10 to the minus 36, or 2 times 10 to the minus 36 kilograms. So a zero with 36 decimal places in front of it. And so what are things we know and love in units of EV? A proton, which we know is very, very, very light, actually weighs almost 1 billion electron volts. And the scalar fields that I care about weigh 10 to the minus 22 electron volts. So when I say it's ultralight, I mean it is, roughly 10 to the 30 times lighter than a proton. Very, very, very light. And these light scalar fields, we believe, exist in the universe, and the dynamics of the field can sort of mimic dark energy or dark matter. So axions are very, very light. Currently, we are trying to come up with different models of dark matter, because just saying that it doesn't interact with light isn't really satisfying. We want to figure out what its properties are. And the axion is one of these models. And so one part of my day job is to come up with predictions for what the sky would look like in a world of dark, where the dark matter is made up of axions, and then match those predictions with the observations that we see. And currently, we are only really able to put limits on how much of the universe could be made of axion dark matter. In most cases, it's currently indistinguishable, so we need to work a little bit harder to think about ways we can detect this elusive dark matter particle. So I talked about dark matter. It's not interacting very much with light, but it could be a field, it could be a particle, it could be something we know and love. What about dark energy? I said the only thing that's common to the two is the word dark, and that's really true. So let's unpack dark energy a little bit more. It's very strange, and if you don't leave here confused and angry, then I haven't done my job correctly, because that's the state of being in which I live a lot of the time, because dark energy is really elusive, and we're trying to understand what it's doing to the universe. So anyone who's older than about a year old, understands gravity inherently. If you take a small child and you hold a ball and drop the ball, they know that the ball will fall to the ground. That's how gravity works. We all are really, really comfortable with that. But what if this little girl dropped a ball and the ball floated away? You would instantly look for some air, some vent of air underneath the feet, or trying to figure out where this could come from. And that is the sense of confusion and disarray that astronomers were in, started to be in, about 30 years ago. So how did this happen? Well, I love using analogies, so I'll continue to do so. But I love to show this image. This is a photo that was taken of New York City in 2012, just after Hurricane Sandy. I happened to live in New Jersey at the time. And one of the things that happened was all of the lamps, the sort of street lights, went out in lower Manhattan. And so if you were trying to jaywalk, which of course nobody should ever do, but if you were trying to jaywalk and it's dark, then what you do is you will use the brightness of the headlamps of oncoming traffic to determine how far away the cars are from you. Now, everyone does this. I don't think I imagine you haven't asked yourself what are the equations that your brain is using to do this, because we all, if we've lived in cities anyway, we're just comfortable with doing that calculation. But it relies on a very important assumption. It relies on the assumption that whoever put the headlamps in the car put them in with the same brightness, which is of course why we need to take our car into the shop to make sure that the headlamps are to code. If the headlamps are not intrinsically the same brightness, then you wouldn't be able to calibrate the brightness that the car appears to be with how far away it is. So I like to think of these as like standardized headlamps. We have these standardized headlamps. And the reason why we need to know distance if you're crossing the street is because you don't want to get hit by a car. But in the cosmos, we want to measure distances to objects so that we can understand the shape and the evolution of the universe. We want to understand how is space changing with time. And the way that I can figure that out is by making measurements of distance along the way. And so I need an equivalent standardized headlamp in space that will allow me to do this calibration. Otherwise, I'll be stuck in the same way that we would be stuck if we didn't have standardized headlamps. Luckily, nature has provided one of those standard headlamps for us. And in fact, in this particular example, we've even provided you with a little arrow of where to look. So in this case, this is the Whirlpool Galaxy. It's a very beautiful galaxy in the Messier collection. And you'll see, if you look at a photo of this taken, this is a composite image taken by astronomer Jeff Hilton. If I switch between this day and the next day, you'll notice the beautiful explosion of SM 2011 FE, supernova that exploded while I was doing my PhD. And normally we don't provide an arrow, but these bright supernovae often outshine the local environment. They're very, very, very bright. And the physics of these stars is it's believed that they explode with roughly the same brightness. There's obviously lots of details we need to figure out, but this provides us with a roughly standardized headlamp in the universe. And so we can measure these objects out to very far distances. In fact, many of the supernovae that we use for our research actually exploded when the dinosaurs roamed the Earth, and the light has taken that long to reach our eyes, which, again, it helps me sitting down when we get these facts. Really, really, really very large distances in time. Most of the things in the sky that we look at are no longer there because the light has been traveling so long to reach us. This is another Hubble Space Telescope image of a supernova in the outskirts of a dusty galaxy that's sort of almost edge-on. And this dust and, the beautiful dust lanes show you this incredible galaxy. But while this image is taken with Hubble, this obviously is just one supernova, and we want to measure many more supernovae to try and accurately constrain distances in the universe so we can figure out what is happening with dark energy. And one of the reasons why we want to do that is because in the late 90s, some of my colleagues made measurements of these supernovae, expecting to see that the universe would behave as we had predicted, in that it would expand, and at a certain point the expansion would be kind of overcome by the gravitational crush of everything in the universe, and the expansion would slowly reverse, and the universe would end in a sort of big crunch. However, in the late 90s, these astronomers, some of whom are my colleagues, they actually discovered that the universe appears to be accelerating. So it's not only continuing to expand, but that expansion is now happening at an accelerated rate. And it directly contradicts what we expect under gravity. And so when I tell you that dark energy is effectively an anti-gravity, I mean that At the moment, dark energy appears to be something that is driving this accelerated expansion of the universe. We don't know what it is. All we know is we can see what it's doing. And so what we need to do is get more and more observations to try and pin down exactly what it's doing, as opposed to just, oh, things are accelerating. But how is it accelerating? What is the what models could possibly be doing this? And so in order to do that, we need to build more sensitive telescopes. So hopefully this will play. Yes. And we're going to play this video. It's only a minute or so, but it's a wonderful promotional video for the Vera Rubin Observatory, and really just hits home how the telescope is going to change astronomy. And we'll start here. This is a quote from Vera Rubin, and who was a pioneer in the study of dark matter, and who really articulated so well that the universe has so much more to offer us. So I'll just play this very briefly.
The night sky, our window to the universe beyond. Immense, mysterious, powerful, quietly beautiful. Cosmic events at the edge of our imagination unfold in the darkness, ready to be discovered. When we look at the night sky, we see into the past. Untold stories carried through space by light, the great historian of the cosmos. Technology has evolved over centuries, allowing us to look farther, to the edge of our horizon. We invented telescopes to explore and cameras to capture these traveling messages. Yet the changing cosmos remains unseen. A new telescope opens its eye and captures it all. The objects that move and those that flash, even those we cannot see with our eyes. Every few nights it covers the sky, finding all that has changed. And within minutes, new glimmers of activity are carried around the earth to anyone waiting to explore them. What will you discover that no one has seen before? It's time to find out.
I have watched that video, maybe 20 times, and every time I get chills. Very, very excited about what we will deliver. So this is the mirror for the Rubin telescope, which was driven from Arizona to a ship where it was shipped to Chile. This was taken before COVID, when integration was starting. You see this giant mirror that goes into the camera. That's on the BBC Manitoba. Everyone would appreciate that. And at the heart of, behind the artificial mirror is an incredible camera. So the Rubin camera has 2,200 megapixels and is the size of a small car. And until just last week, this was the only image I could show you, but actually the Rubin camera is now almost ready to be installed, and this is a picture from a week ago. It really is incredibly large, and you can see the array of CCDs at the back of the camera. And as you heard from the video, it will scan the sky every few days, which will allow us to just discover a ton more of these incredible images. It's useful putting in context just how the sky will look different. So, pre the 2000s, if you did astronomy in the 20th century, you probably used photographic plates, and they were incredible, but they were only able to record certain objects and not very deep. And it was really the revolution, the digital revolution, that started in the early 2000s with the Sloan Digital Sky Survey that allowed us to scan and record the sky at a much higher frequency. of time frequency. The Sloan Sky survey is incredible, it's ongoing, but Ruben will take that one step further. So if you look at this data from the Sloan Sky survey, and now we go to a simulation of what Ruben will see at its depth, you just see the sky starts to sparkle, right? There's so much stuff that wasn't available to us that we weren't able to see. We will be able to see significantly further in redshift, and we'll see hundreds of billions of galaxies over the whole sky. And if you're interested in transient astronomy, as I am, because I'm looking for these standard headlamps, then the sky will start to shimmer in ways that it hasn't before. We have found transient objects before, but normally looking at a small patch of the sky. And now we will just see the sky basically sparkle daily, and we'll detect very many, 10,000 new objects a night, which is totally incredible. So you may ask, well, how do we find them? And this is some work that I'm involved in, because if we have a sky that is glittering with a bunch of transients, only some of them are going to be the headlamps that I can use to measure these distances in the cosmos. Other things will be normal stars that are flickering, or dying stars, or other interesting events that aren't necessarily these cosmic beacons. And so the way we do that actually is, we may think that we have images like this, but really we'll have images more like this. But we take the image of the sky today, we take the image of the sky yesterday, and we compute the difference between them. And that difference will yield the presence of these bright objects. And if I do that as a function of different filters, if I filter out the light that I'm picking up with the Rubin camera, then I can see how these light curves change over time, how these objects change in their brightness as a function of wavelength over time. And this means we'll be able to develop a huge sample of new objects to study the cosmos. With that data comes a lot of complexity and a lot of challenges. And so some of the work that I do has become statistical in nature, because I'm trying to match these observations and come up with the best observations that I can in order to answer these science questions. When I try to describe the challenge to people, I say, let's imagine like I had a fish tank, and I had one or two beautiful giant fish that I could study very, very well. That's like our current sample of transients, or current sample of potential supernovae with these, these standardized headlamps. We have about 5,000 known objects that we use to study the cosmos, and that's great. Ruben will give us a sample more like this. Tons more fish, but I don't know if they're all the right type. And I need to figure out which are the cosmic headlamps that can help me pin down the nature of dark energy, and which are just other interesting objects to study, but not necessarily of cosmological interest. The way I do that statistically is based on a gentleman called Reverend Bayes. He was interested in gambling, actually, in the past, and developed statistical theories that bear his name. So if you've heard of the phrase Bayesian statistics, or Bayes' theorem, refers to Reverend Bayes. And it may sound like, we're getting into statistics, this is way too complicated for a Friday night, but the key idea behind Bayes' theorem is actually really simple. If you told me that everyone here arrived in the lecture hall together by dragon, I would laugh at you. But of course, I could see you sitting there. If I didn't know anything about dragons, if you told me you arrived by dragon or you told me you arrived by car, those are equally probable, because you arrived and therefore that's all I know. The reason why I laugh at you when you say you came by dragon is because I know dragons don't exist. But that's my prior belief. And Bayes' theorem allows us a way to statistically weight our prior belief in something with the data that we see, our observation, which is you are sitting in the room and I can see you on Zoom. And so when I'm applying this to the cosmic beacon example, this supernova example, I need to weigh the information I'm getting from each of these potential transients by whether or not I think they actually are a cosmic beacon or they're just another star that's dying. And that's because I want to always get to this point, which is what is the fraction of the universe made up of dark energy, what is the fraction of the universe made up of dark matter. And with the Bayesian analysis techniques that we've developed, we will actually already be able to do incredible things with Ruben to really pin down that number and really then learn about what is driving the acceleration of the universe. So we'll be able to reduce our uncertainty in the cosmic makeup of the universe with the help of these Bayesian statistics and then the incredible data that we're getting from the Rubin Observatory. So, as I said, astronomy is about building the puzzle picture of the universe. And the Rubin Observatory is going to be a really exciting part of that. I should note that I will use Rubin as a scientist, but one of the key things about this large telescope that's being built is that it will release some of its data, particularly about new objects in the sky, to the world nightly, in fact, almost every minute. And so it also provides an opportunity for people who are interested in astronomy to get involved from the comfort of their own computers and to start looking and playing and finding new things. It really provides an incredible opportunity for all of us to ask our own questions about what the universe is made of, how it's changing with time, and what makes it tick. So I'm really grateful that I can be doing this work and with the support from lots of different organizations. And I'm really, really pleased that I can talk to you this evening, and hopefully you have lots of questions for me. Thanks so much.
When does it go online?
Okay, did you hear that, Renee? When does the telescope go online?
Oh yeah, great question. So the commissioning camera has been installed. So basically we made a tinier version of the big camera with the same mirror to be able to do tests, and that's been installed, and that will start taking commissioning data in 2023. And the Rubin Observatory will see first scientific light in early 2024. So it's really around the corner, which is amazing.
For sure.
We have a question here from the chat and from Facebook, although I think the person's also in the room. Have machos been ruled out as a form of dark matter, and if so, how?
Absolutely. So machos are massive compact halo objects, and for those who don't know the sort of backstory, there is a proposed dark matter candidate called WIMPs, which are weakly interacting massive particles, and so machos are a nice sort of analog, pushback to the WIMPs. The problem with machos is that if you add up how many compact halo objects, so planets, for example, or small black holes, if you add up how many you need, the number is just too large. So dark matter just seems too prevalent for that to be really a viable candidate right now. Yeah, so they're basically been ruled out.
We have a question from the Zoom audience, from Catherine Wright. What do you like most about your job?
We lost Marlene.
She's muted.
You're muted.
Thank you. I get this question a lot from school kids, and I tell them I don't care what your parents do, I have the best job in the world. And I think what I like about my job is that it's very varied and it's very self-directed. So I'm in a research group. I work with a lot of colleagues and collaborators, and we define and talk about what are the interesting science questions we want to answer. It can also be quite scary scary for the same reason, because I need to work a lot independently and ask questions and ask for help and engage with my research. But there's a real joy in being able to go to work and think about really fun questions like, what is time, and what is the future of the universe. And so I'm really lucky I get to do that, and I get to use data as well.
Another question from Ed is, how will the Rubin Observatory and its pictures compare with Hubble and Webb?
Thanks, that's a great question. So the big difference between the Hubble Space Telescope or JWST and Rubin is really the field of view and the resolution. So if you think, and I have an image here with me, let me try and bring it up. Screen again to just show you. So the field of view is what's key here. Okay, we can hopefully see my screen. Okay. So in this picture here, I'm showing you, this is the Rubin while it was being under construction, and the size of the full moon on the sky is about 1/2 degree, and the tiny little speck that you see, that's the field of view of the Hubble Space Telescope. So Hubble can see with incredible resolution. It's has excellent resolution. It's in space, but it can really only look at a tiny part of the sky at the same time. The red circle is Rubin's field of view. So it can look at a much wider picture of the sky at the same time. The individual images that we see taken with Rubin will be lower resolution than Hubble, but of course the Rubin telescope will also be able to take many pictures night after night and get a deeper image of galaxies as well. But they're never going to look as beautiful and crisp as the kinds of things that you've seen with Hubble.
Are there any questions here? Yes.
Yeah, I have a question. The Rubin scope, it sounds like, it's a 3.2 gigapixel camera and doing the analysis for transits and all that. It sounds like it will have a very high data rate. I'm just wondering, are there any new technologies for processing all those data sets and being able to distribute them around the world? So is there new technology for doing processing?
Great question. So just for the folks on the phone, the question is about that, if you have such a large camera and you're taking so many pictures of the sky, do you have to worry about the data rates? And you're right, that is an excellent question, and it's something that really does keep us up at night. So in fact, we around the world are interested and worried about this problem because it really is a very big one. Rubin will produce more data than any telescope we've had in the past, and so it is really important to be able to process that. There are multiple ways we will be processing the data. So some of the data will sort of be processed very quickly right away and delivered to everyone else, and then there'll be sort of curating of larger catalogs and sort of those things on a shorter time scale, a longer time scale. I'm going to share my screen just one more time because these are just extra slides that I have. So one of the tasks of the US, and this is originally built out of the US or Canada, one of the things we're doing actually is I am the PI of a proposal to build a huge data center with Canadian funds to house some of this data and to be able to host it and share it with the community. And so the data rates expected from Rubin are really, really immense. And there will be these huge data centers around the world which will take data from Rubin and then send it out to the communities, because you could imagine, just crashing every server if you try to access the data. It's also a completely different model, so you'll never, it used to be the case that if you observe with Hubble, you could download the images to your laptop and then have a play with them. There's just too much data for you to be able to do anything like that. And so what you'll actually have to do is run your analysis programs on the data facility, like the one we're proposing to build in Canada or the one in the US, and then you'll do that processing and then return the output, rather than downloading everything and then doing the analysis on your own machine. So it's a completely different way of doing astronomy because the data rates are so huge. What that means is actually we need to, this is getting a little technical here, but we need to develop database protocols, networking protocols, so how is the information being passed, what happens if any of the feed drops at any time, and there has to be a lot of redundancy. So the data facility question for Rubin is really, really huge, and we are trying to attract the best minds to help us with this problem to make sure that we can access the data and share it with the public too.
So there is a question on Zoom. Have you received images yet from Rubin?
No, so we're mainly working with simulations of the Rubin sky. So in order to make sure that we're ready, we need to prepare. And so we're simulating the sky. We're actually also simulating some data streams to see if people can handle it with their computation systems. But the commissioning images will start to flow next year, and then we'll see first images from Rubin in 2020, which is exciting.
So I have a question about dark matter. Is there anything recorded where dark matter interacted with what we know as matter and became visible rather than dark?
Very, very good question. In fact, we have a ton of experiments around the world trying to find just that. So when I say it's not interacting, I mean it's actually very improbable. It's not impossible, but very improbable. And in fact, you can build these facilities to try and detect dark matter. One way that you could do it is sort of similar to the way that you look for neutrinos, but basically you go to old mines deep underground, you fill them with special elements, and you try and look for these very rare interactions between a dark matter particle and, say, one of these elements. And these are very rare, but the prediction is that you should get a few events. And if you get those few events, that will tell us about what the dark matter particle could be, because the probability that you bump into one of these, say, xenon particles is dependent on the properties of the dark matter. Now, controversially, if you're interested in some dark matter politics, there is a group in Italy that have been claiming for about a decade now that they have evidence for dark matter detection of a dark matter signal. They developed a special crystal that they thought would be sensitive to dark matter interactions. However, they for a long time put a patent on their crystal design, and no one could reproduce their experiment. And only recently have folks started to replicate the experiment in other places, and so the jury's still out to see if they actually see a similar signal. But these are really rare, and so we need to build a ton of experiments quite deep underground so that you can shield yourself from any other particles that may be zipping around to try and find the ones that are really coming from dark matter interactions. We can also look for them indirectly. If you look at very dense places, for example, look at the core of the galaxy and look, is there any excess light that you would expect at very particular energies? And that excess light could come from dark matter interacting with itself at the center of the galaxy. But again, we basically have upper limits right now.
Thank you. Any other questions from Facebook or Zoom or the audience?
That's a wonderful question. I feel like I definitely need to speak to whoever asked that question. So, so I think Serrata is for the rest of the audience. So Serrata is an initiative. It's the Canadian Initiative for Radio Data Astronomy, and basically it's a platform, a computing platform that processes and serves radio data as a precursor to getting radio data from this Wave Kilometer array, which is also going to be built. And so Serrata was a huge investment and it's a big success. And in fact, I mentioned this very large proposal that we're putting in, that we have put into the Canadian Foundation for Innovation. And it's to build a Rubin data center, but it is expressly actually to couple to Serrata. So we need to, so that we can basically use radio data and optical Rubin data on the same part of the sky, because you'll learn a lot more about whatever is exploding, whatever is going off, going bang in the night, if you can combine data from different sources. But in order to do that, you need to figure out how to make the data talk to one another. Again, the sort of fun behind-the-scenes stuff of networking, database curation, and integration of data sets. So if we get our way, if the CFI funds us, then yes, Serrata will talk to Rubin. It will actually be the beginnings of a pan-observatory Uber-Canadian proposal. So we have named, because everyone loves acronyms in astronomy, we named our data center Candy Apple, which is the Canadian Data Intensive Astrophysics Platform. So if you ever see Candy Apple, then you know we have succeeded.
Tremendous good luck with that and with all your other proposals for data handling and all of the collaboration. I think we'll call it an evening. Thank you so much for your talk and for engaging us with all your enthusiastic answers and I think penetrating thoughts for the future. Take care, Renee. Okay, I think we'll have our break now, and we'll reconvene at, say, 8:45. So, mingle on Zoom and mingle here. We're looking for volunteers who might like to give a presentation. We like to vary beginner sessions. We like to vary what's new. So far, Brian's been doing what's up really religiously. Thank you. And we also like ideas for main speakers. Could be you, could be someone you know, could be someone you thought of, could be a topic you're interested in. So please send us ideas that way. The Loner Scope Coordinator, Mike Caracas, is here tonight. He's been a little busier than we have been in the last few years, so if you're interested in picking out a Loner Scope, please see him. There's a Bino interest group. Darren Hennig has been quite active there. First Fridays are people gathering to look at the sky from outside the Manitoba Museum, and if you're interested in participating on the first Friday of every month, please see Scott or send him a note. We're now seeking nominations for people who'd like to be on council, or if you have an idea of people who'd like to see on council. Brian is chair of the nominating committee, and he's here tonight if you have ideas or if you'd like to say you'd be interested. And believe me, we can always use new ideas on council. If I can be on council, you can be on council. That's really true. The dome is open, and Glenlee had a really good cleanup over the last weekend, thanks to a good dedicated crew. A special mention to Mark Irvine, who was filthy up to the waist at least, and did the worst part of the job before some of us even arrived. But it's all spiffy looking. Please join people tomorrow for members' night out there. Map of the Glenley site is on the back of the Winnicentrics that we receive every couple of months. Council is working on ongoing things related to incorporation and Glenley repairs, making a policy and procedures manual, and coordinating with the Conservancy about the possibility of another dark sky preserve. We have an announcement that Russell Brown will be the Spruce Woods coordinator for the upcoming year. Sylvia Graca did an amazing service for so long, was here 13 years, but I think she lobbied to do it before that, lobbied to improve it, and really a lot of what it is now was built by Sylvia and a really dedicated team. But Russell is now looking for ideas for speakers and I guess a group that will help him take this forward. The RASC calendars are available now. Abdul comes to the meetings and he will gladly take your booking by email or sell you one on site, and the cost is $18, so don't hesitate to contact him for that. Oakhammock Marsh is still having outreach events. I think the admission is free if you do outreach with them on third Thursday, is it? Yeah, third Thursdays. If you come with your telescope and it's clear, then admission will be free. I don't know if they do this when it's cloudy, but I think they have something on. They just don't look at the sky. So there are a number of volunteer opportunities aside from people who are on council. You can volunteer to help coordinate the meetings and the content of meetings, coordinate volunteers and outreach activities. We'd like to have a coordinator for the Explore the Universe program of certificates. We need a new webmaster because people doing it now are taking on additional jobs, and we know what happens when a few people do all the heavy lifting. Things just peter out too quickly. Always need meeting presenters. We do have a finance committee now, at least for the interim. We have Abdul, myself, and Mark Irvine, and we are preparing the budget that will be presented at the AGM. We always need members on the observatory committee and need some volunteers to help train new members on use of the dome and orient them to Glenley. And we're interested in building a light abatement committee to go with dark sky preserve activities. Ideas for nominating committee members and the awards committee. So the finance committee we've already constituted now, but we will fulfill roles that are identified in the bylaw to support the activities of RASC and prepare a budget based on the planning from the work by Abdul over the last number of years and the expenses and revenue that comes in primarily from memberships that we get through national. We would take your recommendations to heart and discuss priorities for council and the center, and work with the treasurer obviously very closely. And members observing night is tomorrow at Glenley. I think it starts at dark, but obviously you can go earlier if you are going to set up. So now we have first speaker Brian Stash. I don't think it's on.
Testing. Everyone hear me? Yes. Okay, so let's see, it takes a while for it to roll. Okay, well, simply we'll talk about what's happening in the month of October 2022, but we'll touch base with November because we do have a lunar eclipse that's happening on November the 8th.
Am I supposed to follow that arrow?
Thanks, man. Thanks a lot. Is it quit? Yeah. Okay. Okay. No. So I can hit that. I see, okay, sorry about that. Let's talk about what's up for October and November. As I mentioned, we'll talk a little bit about November. There's a big event happening there. Okay, we're going to talk about a little about the planets. Okay, so Mercury is not, I say Mercury is a good position right now to view it. It's going to be in the pre-dawn, but as the month goes on, it won't be quite observable, but because it's getting closer to the sun. Venus is too close to the sun to do any kind of observing, whereas Jupiter, its retrograde is slowing down, but not at standstill, whereas Mars and Saturn retrograde is slowing down to the point where it'll be standing still at the month end. Mars brightness will increase a little bit to 1.2, I believe I have here. So let's talk about the months or the events that's going to happen in October. I say there's a lot happening here, but the double shadow transit on Jupiter on the 19th is not going to happen in our hemisphere. It happens roughly, I think, 3 o'clock during the day, so that's not going to be visible. We have the Orion meteor peaks on 21, but there's another meteor shock is going to start on October the 20th. I'll explain more about that later. Of course, we have the new moon on the 25th, and of course, as I mentioned, Saturn and Mars are going to be stationary on the following dates. All right, so let's talk about, I'm going to talk a little bit about Mercury. Okay, as I pointed out here, well, October the 15th, well, midway, it's not going to be observable, but it's in the pre-dawn right now. It's in the dark sky, so if you want to view Mercury, now's the chance to do it. I set it for October the 15th, as you can see here. Later on in the month, it's going to get closer and closer to the sun, so if you're going to view Mercury, now's the time to do it. Now, when I was playing around with this, again, this is tomorrow. I kind of like put around the observatory alert, the members' night that's happening tomorrow. This is going to happen around 12:30 at night, but I'm a big fan of Orion. If you're a new member, that would be one of the targets that we'll try to show you if we stay up that late. But as you can see here, Mars is just going to be a few degrees from the moon, and of course we have Pleiades on top. I'll explain a little bit more about the targets that's going to happen later on. And the Orion meteor shower that's happening or peaking on October the 21st. I think it's a good night because the new moon's going to happen on the 25th. So it's not going to start to rise until 1:30 in the morning. So it happens to be clear, and it looks like the forecast so far looks pretty clear, but we'll touch more about it later. As I mentioned, it's October to the 2nd of November. That's the range of it, but it's going to peak on the 21st. Now, I'm going to mention the other meteor shower that starts October to the 20th. And the reason why I want to mention it because it kind of overlaps. So what does this mean is, well, you have a greater chance of seeing some sort of meteor that's going to happen during the night. This one here has some really high fireballs, but it's only 5 per hour. So, again, I'll touch more about it later. It starts, I think it peaks November the 5th, I believe. So, when I was playing out the model here on the website, as you can see here, I'm kind of a big fan with Starlink. As you can see here, we've got a bunch of arrows here. And that's Starlink. If you haven't seen it, now you know when it's going to happen. So I have it right here about roughly 10 o'clock at night. It's going to happen here. Can we see it? Yeah. So we've got Andromeda Galaxy here, that's M31. That's Pegasus. So these little blue arrows, plus this one right here, is Starlink. If you haven't seen it, you have a good chance of seeing it at 10 o'clock on the new moon. That's why I set the date on October the 25th. During the last lunar eclipse, that we had a while back in May, it was quite spectacular because what happened was we saw a string of satellites, and we couldn't explain what was going on until later. We found out there was, 8 or 9 Starlinks that was coming up, but it was quite a spectacular view. All right, so as I mentioned before, if you're new to astronomy, I kind of list some of the targets that you should, and for Remembrance Night tomorrow night, we'll try and show you some of these objects here. Now, we're losing the core of the Milky Way, obviously, here, but I said around 10 o'clock almost at night here. So we have Hercules, which is M13. We have M57, Capellus, here, the constellation right here. There's a double-star cluster. If you haven't seen it, again, we'll point this out. That's going to be visible for most of the night. I think the designation was NGC 869 and 867, was it? And of course, we have Jupiter and Saturn is going to be up, right? It's almost like due south. And what else do we have? Of course, we have the Pleiades that's coming up. So again, we have a lot of targets, a lot of objects, of opportunity that's going to happen during Remembrance Night tomorrow night. But again, if you're a new member and new to astronomy, of course, I think Scott and I are going to be hosting it tomorrow. So, of course, we'll be happy to show you. The zodiacal lights that's happening, it's going to happen on October 23rd. If you haven't seen it, this is in the pre-dawn, not really the best time to see it. I've seen it after sunset in the fall or in the spring. So, again, if you ever want to know what it looks like, this is what it looks like. It kind of looks like a pyramid of light. It's a little brighter than the Milky Way, but you have to get used to it because you haven't seen it before. It's bigger than you think. So, what else do we have here? Okay, I keep every month I'm talking about the solar activity because, again, snow is coming. I said the S word, so unfortunately. We're blowing the bell curve for this. The predicted values over the actual values are just way high. So what does that mean? We have a greater chance of seeing the aurora. And next week holds, looks like we have some clear skies, and it will warm up by Friday of next week. So if you have a clear sky, I say get out there and do some observing. Okay. Now what I have here is the temperature in this graph here, and I should maybe explain it a little bit more. Okay, so this line represents 0. So you can see that it's going to be kind of cold over the weekend, and it's going to drop way below 0. But as it progresses throughout the whole week, Friday is going to be in the mid-teens. And it does drop down a little bit on Saturday morning or Friday morning, but then it's going to creep back up. So there's a greater chance, like we're still going to have some good weather. And here's the clouds. This little bar here, this is supposed to be gray. I don't know why it's not gray here. It's supposed to be gray. That represents the cloud coverage. So you can see here, we have some openings here for clear skies. This changed. This last night was something entirely different, but this weekend, it doesn't look very good for Members Night. We're going to have a little bit of snow, a little bit of rain, but cloud coverage, it still looks like it's still going to be still quite high, so we're not going to have any clear skies, but we'll see tomorrow. So this is the date where the meteor shower is going to happen. Again, that kind of changes, but again, Friday night, there might be a chance to see it. All right, as I mentioned before, we have that total lunar eclipse that's happening on November the 8th, but it's not going to happen until towards 2 a.m. in the morning. It's not like back in May when it started right after sunset. But since it's happening in November, I don't know how warm it's going to be. So, but if it turns out to be a warm night, well, 2 o'clock is really not that bad. But how does it look? Well, according to the model, I kind of like put this here. The moon's in dead center right here. So it's pretty high, I would say. But again, there's a lot of things happening at 2 o'clock in the morning. We have Orion. We have the Orion Nebula here. We have the Pegasus here. We have Andromeda Galaxy, of course, Cassiopeia, with my favorite 2 double star cluster. Jupiter obviously is setting here at that time. So yeah, I would say that for the next couple of weeks we have a great chance of seeing something. So if you're not busy like me with a bunch of projects at work, weekend would be the ideal place for me. So that's all I have to say for what's up for October 22nd. Thank you.
Brian, just want to clarify, if it's cloudy tomorrow,
Yeah.
which it may be, how will people know that there is or is not a member night?
Well, we should have sent an announcement out, right, Scott?
We'll send an email through the.
Usually, I think in the past what we did was by 4 o'clock, 3 o'clock, if it looks like the weather's not going to clear up, we'll send an email to everyone in the group saying that it's going to be canceled. So keep it fair. But we want to keep it open because who knows? The weather can change. So again, I'm not going to call it right here and then that it's going to be cloudy tomorrow because we just don't know. All right? So again, we'll let you guys know tomorrow if it's going to happen.
And then orbiting that is a small moon around an asteroid called Dimorphos, and it's significantly smaller. It's 163 meters across and weighs a paltry 4.8 billion kilograms. And so the mission was aimed at impacting Dimorphos, so the small moon, in the hopes of slightly altering its orbit. So it wasn't going to remove it, it was just going to change the orbit of Dimorphos from the way that it was orbiting around Didymus. And so DART is about the size of a refrigerator, and so it got launched, and then launched kind of behind it is another companion CubeSat called Lycia Cube, and so that stayed in orbit around the asteroid pair and watched the whole shenanigans, the whole impact. All right, so DART's goals, this is humanity's first test of asteroid deflection technology. And so this is a proof of concept that the movie Armageddon might be able to work. Thank you. But really, it's a proof of concept for testing the deflection of Earth-threatening asteroids by changing its orbit. And so we know from Earth's cratering history and the extinction of the dinosaurs that Earth has been hit by asteroids before, but this is the first time where technologically we're able to maybe do something about it. The other bonus science content of such a mission is that we can learn about the surfaces of the asteroids and about the asteroids themselves. And the reason asteroids are so interesting is that they're one of the least processed bodies in our solar system. And so we think that they still have the composition and the structure that would have been present in the very early solar system before our planets were formed. And so if we can learn about asteroids, we can learn a lot about where our planets came from in the very beginnings of our solar system. So the diagram I have here, in white is the original orbit of Dimorphos, and then the yellow line represents the new orbit, so the slight deflection. So you can see we're not blowing anything up, we're not removing any orbits, we're just slightly modifying it to see if we can do that with a fairly small spacecraft. This is a YouTube video from NASA Live TV. This is very exciting. I'll start playing it. See if it works. I'll mute it because you don't need competing sound sources. I don't know if it's muted, but this was broadcast live. You can see a team that has spent years planning this mission out. This is a live, well, it was live on September 26th, but it was a live camera from DART. And so this large body on the bottom left is Didymus, and this little body here is Dimorphos. And so the reason you're seeing steps that kind of jump is that you're taking an image and then sending it back to Earth, and then taking an image and sending it back to Earth. So you can see that we're moving closer and closer to Dimorphos. You can see the team, that lady is wringing out her hands. She's very nervous. And so late in the evening of September 26th, I'm not going to spoil it for you, but DART made impact. I am going to spoil it for you. DART, this is slower than I hoped. DART made impact with Dimorphos. These asteroid pairs were chosen because they were never a threat to Earth, and so there was no risk of nudging it a little bit into Earth orbit. So it was really a proof of concept. And so now we can see we're headed kind of straight into Dimorphos. We're starting to be able to see some of its surface. This is the first time ever that we've been able to see its surface in such detail. It was hypothesized to be a loosely held together jumble of rocks and boulders, but its exact composition is still a little bit of a mystery. So you can see my computer tried to auto-caption this, and it said dark red. So maybe like a whole grain or a multi-seed. So you can see the boulders. It's got lots of different sizes of rocks and dust. There's no missing it at this point. So the team is jazzed. And there we go. Collision. Very exciting impact. So this is lots of people are elated. This is obviously years and of Dimorphos compared to the vastness of space. This is really an incredible accomplishment. Okay, so as exciting as the live camera was, we also got some really great observations from the ground. So this is, I thought this was really neat, but this is observations from, I don't know how to pronounce this, Winnipeg, I assume, observatory. And so this shows the collision from the ground, and this is data taken over half an hour. Whoop. No. There we go, let's play it again. So it's data taken over half an hour, compressed into a few seconds, but you can really see this cloud of ejecta coming off of Dimorphos as the asteroid hit. And the Atlas Observatory in Hawaii has a similar video. And Atlas is, well, I forgot the acronym, but it's a good one. Look it up. It's something like the Last Defense something. It's worth looking up. I'm sorry, it's slipping my mind at the moment. This impact is also significant because Hubble and the James Webb Space Telescope both observed it. The James Webb was not designed to follow something that's moving very quickly like an asteroid, so that in itself was a technical feat. But this is the very first time that those two telescopes looked at the same thing at the same time. So it's significant from like a technological observing coordination point of view. But both of them also observe at different wavelengths. So this is images from Hubble in the optical wavelengths, so what we can see with our eyes. And so the image on the far left is Dimorphos 22 minutes before impact. The one at the center is 5 hours after impact, and the one on the far right is over 8 hours after impact. And so what was observed is you can see a brightening of Dimorphos, and so the brightening was observed to be about 3 times its previous brightness, and it lasted for over 8 hours. So Dimorphos must have puffed up. It was reflecting a lot more sunlight, and it stayed very bright for several hours after impact. We can see bright rays of expanding plumes. So there's a ray that kind of comes off from the left. That's where dark hit Dimorphos. And so we get these rays that come off, and then it's hard to see in this this image, or this resolution, and I apologize, but the rays are kind of curved, and that's kind of a mystery. So that's some job security for astronomers. We need to figure out why that is. But we're getting a brightening, and we're getting rays of material that are shooting off of Dimorphos. The equivalent image from the James Webb Space Telescope shows also a brightening and rays and beams of material coming off of the asteroid moon. And so we can see wispy plumes of material drifting away from the point of impact. And so that's good that we're seeing the same thing. There's going to be follow-up observations that are planning to get more information about the composition. And so by comparing the images from the James Webb Space Telescope and Hubble, depending on which one is brighter, you can sort of determine whether there's more dust or more rock that has come off. And so you can determine essentially the size of the particles that made up most of the asteroid. So that'll be really interesting. There are also going to be some follow-up observations with the James Webb and the spectroscope to try and determine what the dust is made out of. So that'll be really great. So I mentioned earlier LICIA, which is a nice nested acronym. So the Light Italian CubeSat for imaging asteroids, LICIA Cube. So just throw a cube in there. So it also observed it. And so here we can see the impact at 2 different times after impact. So this is Dimorphos, this is Didymus. And so LICIA is observing from very nearby, but kind of far enough back that it's not going to be impacted by any of the debris. So about 55 kilometers back, you can see that as the outflow from the collision expands, it's starting to really expand. So this I thought was a really nice image where each of these nested squares is just shown at a different contrast to really highlight the filamentary structure of the material. So there's nothing, so these are all just images that have been retouched a little bit differently so that you DART is a huge success. DART slammed into Dimorphos at a casual speed of 22,000 kilometers per hour. The pre-impact orbital period of Dimorphos around Dimorphos was 11 hours and 55 minutes, and the impact was able to reduce that by over half an hour. And so the new orbital period, based on preliminary data since the 26th, is 11 hours and 23 minutes. And so NASA, when they had originally been like, what's a success? Their definition of success was, if we can change the orbit by over a minute, it'll be a big success. And so they managed to change it by half an hour, which is a huge success. And so they think that it's because there was so much ejecta that came off of the asteroid that it really changed the momentum more than just the impact itself. The orbit has also moved closer to Didymos by tens of meters, which is not a huge amount, but it's pretty significant. And so this is a proof of concept that kinetic redirection could work, provided it was initiated early enough and the target isn't too massive. So some of the other science that comes from this impact is that, so it tells us whether such impacts can change the orbital parameters of asteroids. We can start to quantify how much material came off of Dimorphos and how fast it was going by studying how much that ejecta spreads. And that gives us some information about the total mass of Dimorphos and its gravity and how tightly bound the material was to each other. And then the James Webb Space Telescope is going to be doing follow-up observations to determine chemical composition, and the differences between Hubble and James Webb will tell us kind of the difference between rocks and dust. And so this is another image here of Dimorphos long after, this is a much more recent one, but long after the collision, you can see that the debris is kind of starting to form a tail. Next slide, please. Next. It was going so well. There we go. Sorry, it's because you got up. Your computer knew. Okay. So it also allows us to learn about the surface of Dimorphos. And so Dimorphos is thought to be similar to some other asteroids that are about the same size. And so they think it's a pile of loosely bound rocks and rubble. And so if that's the case, then the estimated crater size should be about 10 to 20 meters. But it might be larger, and that'll give us information, or smaller, and that'll give us information about how the asteroid is constructed. And so Lucia is going to keep taking data and give us more information about that. There's also a 2024 follow-up mission run by the European Space Agency called HERA that will launch to study the pair of the asteroids to study the system more in depth. Oh. Thank you. Yeah, I appreciate the chuckle. And so part of the reason is there are more than 27,000 near-Earth asteroids, none of which are currently out Earthbound. But to quote the HERA mission manager, Ian Carnelli, Dimorphos is the first celestial body to be measurably moved by humankind and ultimately to protect ourselves from space rocks that could one day do the same, impact us. So it's very exciting science coming from DART. I look forward to a lot of the follow-up measurements. My next I couldn't do what's new without mentioning the James Webb Space Telescope. I just couldn't. So forgive me for going over time. But I wanted to talk about this newest image from a Wolf-Rayet star. And so a Wolf-Rayet star is a really bright, very hot star with a really dramatic, super fast wind. These tend to be stars that are past the main sequence stage, so they've already burned up all of their hydrogen, and they're fusing helium into heavier elements. So not only are they really hot and have a very strong wind, but they also have a lot of heavier elements. So they are more rich in heavier elements than the typical star. And so what that means is that when they blow those heavier elements away, they're blowing carbon and silicates away from their surface. And so they're a lot more prone to forming dust than regular main sequence stars, or stars like our sun. And so what this image is showing is a Wolf-Rayet 140 is a binary pair. So it's two stars orbiting each other, and these orbiting stars are creating dust shells, which we are seeing as dust rings, And so in this James Webb image, it's a composite of 3 different colors at 3 different infrared wavelengths. So it's 7.7, 15, and 21 microns. So it's a color composite, but you can really see these rings of dust that are like tree rings. They're just incredible. I've already said all of this. I apologize. But you can count 17 dust rings here. And the stars, which are binary stars, will create these dust rings every time they're closest to each other. And that happens once every 8 years, based on their orbital parameters, which means that there's over 130 years worth of dust rings here, which means that these dust rings are not only frequent, but they are long-lasting. And so that tells us that there's a good chance that Wolf-Rayet stars can blow dust far into the interstellar medium and might enrich the interstellar medium with heavier elements. So here, the medium resolution spectroscopy mode on the MIRI camera on the James Webb Space Telescope obtained the first spatially resolved mid-infrared spectra of dust-forming Wolf-Rayet stars. So the Keck telescope actually has, in the early 2000s, made some observations of a ring, dust ring around a Wolf-Rayet star, but it was only one of them, so the 17 is really quite new. And it also directly probed the chemical signatures of the dust shell, so it took an image and it also took a spectrum. And so there were some prominent features at 6.4 and 7.7 microns, which indicates that the dust is primarily composed, primarily of compounds consistent with polyaromatic hydrocarbons, PACs, so those are long chains of hydrocarbons, which are kind of prebiotic molecules, so that's really interesting. Sorry, I tried to click next. There we go. Oh, I went too far. Okay, yeah, so with the combined results from the James Webb Space Telescope, 2 cameras, so we now have evidence that Wolf-Rayet binary stars could be an important source of carbon-rich compounds that enrich the interstellar environment from our galaxy, and galaxies like ours, which could eventually lead to conditions that could lead to life on other planets. That's all I have for you today. Thank you very much.
Any questions for Danielle? It's kind of cool that you've got 17 or however many replicate data sets you can test. You can do all kinds of things because you've got so much data that reproduces itself.
Yeah, it's interesting that they're really regular. I didn't show it here, but there are some simulations that almost exactly predict the data. Yeah, just like clockwork. It's really neat. Yeah, very cool. Thank you.
How many people watched the dark happen when it was going?
Oh,
That was
nice.
such an exciting.
Yeah, great, thank you.
Okay, I think that we have. Where are we? couldn't get calendars